today's notes are on work and energy. We're going to focus on work in the beginning. So it says work is done when a force causes an object to move. So that really isn't enough of a description, so this next paragraph is hopefully going to be a little bit more helpful. So work provides a link between force and energy. To be specific, work is the product of the component of a force and the direction of the component it causes and the magnitude of the displacement. So that's like, whoa, that sounds like a lot of words. So what that's trying to say is that if there's this force that's being applied here, right, it's not the magnitude of this force that causes the work. It's only because this box is moving horizontally, it's only the component, that horizontal component, that's the force that's going to contribute to the work being done. So the force and the direction of the component it causes and the magnitude of the displacement. So it's going to move to the right, so whatever this R value is, and notice it says magnitude, so it's a scalar quantity. You don't care about direction. And it would just be this green force. It wouldn't be whatever the magnitude of this red force is. So back to our statement. For work to be accomplished, a force has to move an object, and the force and displacement have to be in the same direction. So if you lift a book a distance of 1 meter, you have done work on it, right? If you lift up and it moves up, then you've done work. If it was falling and you lifted up to cause it to slow down and stop, you would have also done work on the system. So as long as it's moving in the same plane, essentially. So if you're applying a force horizontally and it's moving left or right, you're doing work. And if you're applying a force vertically and it's moving vertically, then you're doing work. Now it also has to move. So if you hold a book, a heavy book, stationary at some height above the floor, you have done no work on it. So, which seems kind of weird, because if you have a heavy book, it's hard to hold it on the floor. It feels like you're doing something, right? You can't hold it there forever. So you really need to understand what work is. Yes, it's hard to hold a book there, but you're not doing work on it, because work is really this process right here, and it says, right, this process of changing energy from one form to another. So if an object is sitting on the ground, right, it basically contains no energy. If you lift that object above the ground, now it has gravitational potential energy. Well, how did it get there? How did it gain that energy? If you do work on it, you give it the energy. You took the chemical energy from your body and you transferred it. By doing work, you transfer that energy to the object, and now the object possesses that energy instead of you. So the equation looks a little different than last year. Last year it just said work equals FD. So now we have this change of R. Remember, this is going to be magnitude. We're not going to put in direction here. And then the cosine theta, if you look back to our diagram, right, this whole cosine theta is because you only want the component in the direction it's moving. Now the cosine theta is just generic. Realize it could be sine theta depending on what angle they give you. If this box was moving vertically, then it would be the sine of theta instead of the cosine of theta. So it's a place to start, but don't blindly use cosine theta. So let's see. Example. For a force is applied to a crate at an angle of 25 degrees. The crate is dragged across the deck a distance of 2.5 meters. The amount of work done after it has been moved is 1,210 joules. What was the applied force? So that's simple. Work equals F, change in R cosine theta. Because the 25 degrees is from the direction it's moving, right? It's moving horizontally, and this 25 degrees, assuming it's measured from that horizontal direction, then you're just rearranging the equation, plug in your numbers, and you've got your force, right? You need a 530 Newton force to do 1,210 joules of work. Okay, let's see. So the work done by a force is 0 when the force is perpendicular to the displacement. So like circular motion, right? The net force is a centripetal force. It's always towards the center, yet the motion is perpendicular to that. So because it's moving in a different direction than the force, right? Those forces are perpendicular, then you wouldn't do any work. So the Earth, right, keeps the moon in orbit. That force of attraction between the moon and the Earth is causing it to go in a circle, but because that force of attraction is towards the Earth for the moon, and it's not moving towards the Earth, essentially, it doesn't do any work. So if there are multiple forces acting on an object, the total work done is the algebraic sum. Right? So if you have one object putting work into your system and another object taking work out of your system, then you would subtract them. If they're both putting work into your system, you would add them, and so on. So it says it's sometimes easier to find the net force and use that in the equation for work. So instead of finding the, let's say we're back to this example up here, and you have something doing work here. Well, let's say there's friction. If there was a frictional force, that would be taking work out of your system. So instead of finding the work done by this pulling force and then the work done by taken out by the frictional force and adding them together, you could just find the net force between these two and then use that into your equation. Work equals F change in R. Okay, work is positive if the displacements are in the same direction. So if you're pulling to the right and the object moves to the right, you're giving that object energy, and basically it would be kinetic energy, right? You do positive work and therefore the object gains energy. Let's see, where is it in there? Okay, so negative if the force and displacement are in opposite directions. That's usually like, if you think of friction, right? Friction's usually going to do negative work. It's not going to give your system energy. It's going to take energy out of your system. So it's usually, if the object's, like our example up here, the object's moving to the right, yet the friction is acting to the left, so it's taking energy out, not adding energy to it. So work can be done by friction. The energy lost to friction by an object goes into heating both the object and its environment. Some energy may be converted into sound. So basically it's, if you remember from last year, it's that dissipated energy. It's leaving the system and going into the surroundings and possibly the object in the form of heat. So first example. An Eskimo returning from a successful fishing trip pulls a sled loaded with salmon 5 meters. So I'm assuming he is going from here to here, right? He's pulling this way and you travel 5 meters. The total mass of the sled and the salmon is 50 kilograms. The Eskimo exerts a force of 120 newtons. Now again, notice that 120 newtons is here, so it's not all of that 120 newtons is not directed in the horizontal motion, which is the way that sled is going to move. So we are going to have to go through and find only the horizontal component of that force, because that's the only part of the force that's going to do work. So it says the coefficient of friction between the sled and the ice is 0.2. How much work does he do on the sled if theta is 30 degrees and he pulls the sled 5 meters? So if I want to know the work that he does, I'm only going to use the force that he's applying, which is this green force. So if that's our equation, right, for the P is for the person, I want the force of the person and the distance of the person, essentially this F cosine theta is going to find this green force here, this component of that pulling force. So 120 cosine 30 gives me this green component of the force, and the 5, of course, is the distance that it travels. So what does that equal? 519.62 joules. So the person is putting in 519.6 joules of energy into that system, which in this case is the sled. So part B, how much work is dissipated by friction? So thinking sum of forces, right? We know that the normal force up is going to be equal to the weight down, but not just the weight down, because you have the y component to this pulling force is also pulling up. So both Fn and F sine theta are pulling up, and the weight is pulling down. So we know the weight, right? If it's a mass of 50 kilograms, then it's 50 times 10, and it's down, so it's negative. The 120 sine 30 gives us the y component to this force, which gives us a normal force of 440, and we need that normal force to find the frictional force. So using our equation for friction, right, it tells us that mu is 0.2, and so we have now the frictional force, and we can figure out the work. Right, so work equals our FR again, and so 85 times 5, it comes out to be positive, but really when you're thinking, this is adding energy to your system, right, and this WF is taking energy out of your system. So for part C, how much energy does the sled gain after it has moved 5 meters? Well, it gained 519, but it lost 440. So the total change in energy, it gained 79.62 joules of energy. So moving on to energy instead of work, right? Energy says if something has energy, it has the ability to do work. That's the generic, definition you find in a book. So think of it this way. If an object has energy, it has the ability to change its surroundings, right? You have energy, that means you can change the surroundings. You can heat up the surroundings, your body. You can move objects around. You can give your energy to something else, and that's going to cause the environment to change. So if you have energy, you can change your surroundings. It's a scalar quantity, so everything that you punch in, whether it's up, down, left, or right, is all going to be positive values. So like gravitational potential energy is mass times gravity times height. Well, it's the acceleration of gravity, which is down, and height, which is up, which would be a positive value. You just put in all of those as positive. The acceleration of gravity isn't negative 10 anymore, it's just 10. You can get negative energies, but it's only when you're talking about a change in energy. So if you started with 100 joules of energy and you end with, let's say, 80 joules of energy, then your change in energy, right, would be negative 20. So it's not that you have negative 20 joules, it's saying you've changed by negative 20. That's the only time you're going to see negative energy values. Now work can be negative, right? Positive if you're putting energy in, but a negative work if you're taking energy out of your system. But all energy is positive. So energy comes in vast array of types. We're basically going to use the same types we used before. We're going to use kinetic energy, and we're going to use a couple forms of potential energy. We'll get into other types of energy second semester, but right now we're just going to concentrate on the same ones as last year: kinetic, gravitational potential energy, and elastic energy, which is a type of potential energy. So kinetic energy, right? This is the energy of motion, so we know if an object is moving, it has kinetic energy. Let's see. So our equation last year we would put E sub k. Now if you look on the equation sheet, it just says a capital K instead of that E sub k. You can still use E sub k if you want. Just realize on the equation sheet this is what it looks like. Remember, all energy is measured in joules, right? Your mass is kilograms and your velocity is meters per second. It has to be in those units to get the units of joules for energy. There's other forms of energy. There's calories is another measurement of energy. It's just the standard that we're going to use is joules. So when an object is given kinetic energy, right, by applying a force to it, you're going to do work on it to give it kinetic energy. The amount of work required to do this, ignoring friction, is equal to the kinetic energy. So an object sitting there has no energy. If there's no friction and you apply a force over, let's say, a meter, and that causes it to accelerate, right? According to Newton's second law, the net force will cause it to accelerate. The force that you applied over that 1 meter, let's say that equals 100 joules of energy. That means you did 100 joules of work and therefore now has 100 joules of kinetic energy. Work is how you transfer energy from object to object or from type to type, from kinetic to gravitational, things like that. We can say this is in a more fancy way. We say that the net work done on an object by a net force is equal to the change in kinetic energy. So this is where you could have this could be a negative value here, right? Because it's always final minus initial. So final energy minus initial energy, and you might get some negative change if the object, let's say it's an object sliding across the floor with friction, right? It's going to slow down over time, therefore it's going to lose energy. It would have a negative change in kinetic energy, and that's because negative work was done. Energy was being taken out of your system because of that frictional force. I believe it's easier to think of this as a conservation of energy problem where your initial energy plus work equals kinetic energy. Now last year, if you remember, we didn't really use work in an equation. We would use, it's hard to write with a mouse. Right? We would use E dis over here on this side. Well, what ends up happening is it can get kind of confusing when you're adding energy and losing energy. This E dissipated we always put over here as a positive value, but if you think about it, if let's say friction is doing work on your system, that friction is taking energy out. So let's say this work done by friction is negative 100 joules. Well, when you move it over to the other side, it becomes positive 100, and essentially that's saying how much energy your system has lost. So using this whole E dis probably isn't the best idea anymore. You can still do it, but you're better to put work over here on the left side and think of it in terms of positive work is adding energy, negative work is taking energy out. Right, so we said work is positive if the system gains energy and it's negative if it loses energy. So again, try to get used to putting this work on the left-hand side of your conservation of energy equation compared to doing this whole E dis that we were doing last year. Okay. Another example problem. The driver of a 100-kilogram car traveling on the interstate at 35 meters per second slams on his brakes to avoid hitting a second vehicle in front of him, which had come to rest because of congestion, right? So traffic jam. After the brakes are applied, a constant friction force of 800 newtons acts on the car. So you can see it's acting, it's moving to the right, but it's acting this frictional force to the left. So it's going to be taking energy out of our system. Ignore air resistance. A. At what minimum distance should the brakes be applied to avoid collision? Well, you want to end with no energy, right? You want to end not moving. So all your energy needs to be dissipated, or something needs to do negative work on your system to take all that energy away. So you have kinetic energy, and then you need this negative energy over here to take it out of your system. So it kind of depends on when you want to put the negative. You could say K minus work of friction equals 0 and put the minus in here, or you can wait till you plug in numbers. It doesn't really matter. There's no accepted way of doing it that makes one way more correct than the other. So punching your numbers in, remember mass is in kilograms, so it's 1,000, right? Not 10,000. So 1/2 mv squared minus, because it's energy being taken out, and this is that work, so it's just Fr. This force is not at an angle, so I don't have to worry about the cosine theta. And the R comes out to be 75.56, right? So you have 76.5 meters to stop, otherwise you're going to hit that car. For part B, if the distance between the vehicles is initially only 30 meters, at what speed would the collision occur? Well, you're moving, you still have all this energy initially, just like before. You're going to lose energy from hitting the brakes, but you only go 30 meters. So at the end, your energy isn't going to all be dissipated. You're still going to be moving, and that will be, whatever this velocity is, that'll be the velocity that you hit the car with. So plugging in your same initial kinetic energy, right? Let's see, this should be negative, not positive. So you're going to lose this much energy due to friction, which gives you a velocity at the end, right? We've slowed down. We were going 35, now we're going 27, but you're going to hit that car going 27.929 meters per second, so you're going to end up obviously getting in a car accident. Let's see. Moving on to potential energy. So potential energy is stored energy, right, from either from its position, like gravitational potential energy, or from something that's deformed, such as elastic energy. Let's see, there are many ways that energy can be stored. An electric battery represents stored energy. That's something that we're going to get into second semester. Water piled up behind a dam, that's essentially gravitational potential energy. Chemical bonds, of course, store energy. We're not going to get into that. That's more of what you're talking about in nuclear reactions, right? There's energy stored in those molecules, and then when you start breaking them apart and forming into other chemicals, there's a release of energy. That's the nuclear part. The type of potential energy that we will be interested in has to do with the energy of position, so gravitational potential energy brought about by gravity and by a spring being compressed or stretched. So same types of energy as last year. First, let's look at gravitational potential energy. When an object is lifted to a height above a reference frame, now what is this whole reference frame? Why doesn't it just say above the ground? Right? It says when an object is lifted to a height above a reference frame, work is done on an object and the object gains potential energy. The energy it gains is equal to the work done on it. The standard form for energy, and you'll see that in a minute. So let's get down to this second part. It says when solving potential energy problems, the reference frame should be chosen to simplify the solution. So you can choose where the gravitational potential energy is 0. So let's say it's something, and I can't really draw because I'm using a mouse here, but let's say this is the ground and there's some sort of spring that's compressed, and then there is a box that's on the spring. Well, there's no need to say that this is a height of 0. You can choose to make this as a height of 0. And if you do so, that means that initially there's no gravitational potential energy. So by basically choosing your reference frame, or essentially where you're going to say the height of 0 is, it makes it sometimes easier because you can start off with a potential energy of 0. Or, if something, let's say it's a stunt diver diving off of a building. He doesn't land on the ground, he lands on some big air mattress cushion deal that's above the ground. Right? Well, you can make his final position 0, the height of 0, so he ends with no gravitational potential energy even though he's above the ground. So you get to choose what makes it easy for you. So it's usually easiest to label the bottom position as 0, and then all other displacements are measured in reference to this 0 position. And you'll see in some example problems where that becomes more clear and becomes a little bit, it does make the problem easier. So back to the equation. Last year we put we put E sub g for gravitational potential energy. Now the U is the symbol that's for all different types of potential energy, and then the subscript tells you the type. So UG or US for spring, or UEL for elastic. And then when we get into electric potential energy, you'll see some other subscripts down there. So of course M is mass, G is the acceleration of gravity. Remember, you're just putting in 10, don't put in negative 10 because it's scalar. And then your height is whatever height you are above your reference frame, or your height of 0. So another major potential energy area is spring. You squeeze a spring, you can compress it. It wants to get back to its original shape, so it can exert a force once it has been compressed, right? And the same thing happens if you take that spring and stretch it out. So a force to compress a spring is proportional to the displacement. Mathematically, F equals kx, where F is the force, x is the displacement, and k is known as the spring constant. Right? This is what we just did in the lab the other day. So you guys came up with that equation. So the spring constant is unique for each spring, and the spring constant has the units of newtons per meter. Right? Think of, if you forget the units for k, just think of this equation. If you move the x over, right, k equals F over x. Well, F is in newtons and x is in meters. So the amount of force it takes to compress a spring is equal to the force the compressed spring can exert, and this is known as Hooke's law. So that's what we were talking about yesterday, that this is the actual equation for Hooke's law, where you have now this negative symbol in here, right? Because if you compress a spring to the left, then the spring, the force that the spring exerts, is going to be to the right. They're in opposite directions. And so that's what this negative is, just kind of telling you that the displacement and the force are always opposite, right? If you, let's say you stretch a spring out to the right, the force is going to try to restore it to its shape, so the force of the spring would be to the left, again in negative directions. So when you put in this x, you're thinking absolute value, you're not putting direction in there. So the minus sign, right, simply means that the direction of the spring force is opposite of the direction it's compressed, which is what I was just saying. Okay, well, the AP test loves graphs, so this is a new type of graph to look at. Work and displacement. The work done by a system can be easily found by analyzing a graph of force versus displacement. So here's a simple graph for a constant force acting over a distance. The work done is simply the area under the curve. So now you have area under the curve, similar to what we were doing in the other graphs. So if you can find the area under a force versus change in position graph, then that force is going to be equal to the work, which really, if you think about it, work is force times distance. Well, the y-axis is the force and the x-axis is the distance, so it's pretty easy to make that connection there. The work done by a 4 Newton force acting over a distance of 6 meters would be the rectangular area shown on the graph to the right. Since it's a rectangle, the work would be height times width, so F times X, right? So 6 times 4 equals 24. So you know that there was 24 joules of work done. This is a graph of force versus displacement for a spring. So notice that as the spring is compressed or stretched out more and more, the force increases. It's not a constant force. The curve is a straight line, the y-intercept is 0, and the slope is the spring constant. So because the force a compressed spring applies varies, see if we cannot use the equation work equals Fr to find the work. Right? The only way you could use that equation is if you use the net, or sorry, not the net force. If you use the average force, then you could use that equation. This is the #1 mistake I see in this unit. People use W equals Fr on springs, and it does not work. It'll give you the wrong value, right? Because this has to be the constant force applied for the distance over the distance of R. So again, the only way you can use this for a spring is if you go through and you put in the average force here. Otherwise, you are guaranteed to get the wrong answer. So if you use there we go. Got to put in the average force. Let's see, the work done in compressing the spring a certain distance is simply the area under the curve, right? And it's a triangle, so it's 1/2 base times height. So if you think about it, 1/2 of the height essentially, right? 1/2 and the height, that would be the average force, and then B is the displacement. But the force is a function of the displacement, right? F equals kx. So plug the value of F into the area equation along with x as the base, and you get work equals 1/2 kx squared, right? Because your 1/2 base times height, well, your base was the x and your height was the force. So essentially, right, you had 1/2 force times x. You've just substituted this in for the force to get work equals 1/2 kx squared. Well, if you look at that equation, hopefully that looks familiar. Right? That's how you know how much excuse me, how much elastic energy is stored. Right, so the potential energy of a spring is 1/2 kx squared. And I think that's it. That should be enough to get you through the first homework problems. So I know I moved through it kind of fast, so I will post this online also in case I went too fast and you missed something and you want to kind of revisit it and listen to a little bit. Otherwise, make sure you ask me tomorrow.